Hi, it's Moser, and this is going to be a walkthrough sample problem 4A in your Holt Physics textbook. We're starting to calculate net external force on objects. So, Derek, leaving your physics book, leaves his physics book on the top of a drafting table, which is inclined at a 35-degree angle. Free body diagram that's given shows the forces acting on the book. Find the net external force acting on it, and determine whether or not the book will remain at rest. In other words, is the net external force equal to 0 or not? Though the book has given us the free body diagram, I find that it's always useful to redraw the situation. And I've labeled the forces acting on it, taking a few little shortcuts. Force of table on book becomes force TOB, and force of gravity just becomes force sub G. All right, now, notice that two of these forces are perpendicular to one another. One is not. Because this thing is an incline, the force of the table on the book and the frictional force, while those things make a right angle with one another, gravity is a whole different ball game. So how do we deal with that? We deal with that by taking the normally perfectly horizontal x-axis and tilting it to match our table. What this allows us to do is only have one force that we have to resolve into components on the x and y axis. The other two are neatly, under this arrangement, already oriented on the x and y axis. So, when we start out with net external force, we first have to find the sum of forces on each axis. The sum of forces on the x and the sum of forces on the y. That sign in front of the f sub x or an f sub y is sigma. It's a mathematical symbol that I draw really badly. I challenge you to do better. This is a lot like non-perpendicular vector problems, where we were finding the total displacement on the x and the total displacement on the y. In this case, we're just finding the total force on the x and the total force on the y. So let's get started with our y-axis. I'll tell you why we started with y in a little bit. So in general, the sum of forces on the y-axis is equal to, really, it's that simple? Yes! All the forces up minus all the forces down. And I find that that's a useful thing to write down for myself at the beginning, just in case somewhere I freak out and have a brain freeze and can't think of what to do. Forces up minus forces down. Pretty easy. Well, in this case, what are our forces? Well, our force up is the force of the table on the book, currently known as force TOB. And our force down, well, gravity's always down, right? In this case, part of gravity is down. One of the components of the force of gravity is directly in opposition to the force of the table on the book. That is the component of the gravity that we want. So, there, I've redrawn that with the components of our gravity in. So, sum of forces on our y equals the force of the table on the book minus the force of gravity on the y. What is the force of gravity on the y? Oh, well, it's the force of gravity times the cosine of that angle. Whoops, that shouldn't be there just yet. So, what is that angle? That little one that's got the little red arrow pointing to it. What is that angle? How can we figure it out? I got a trick for that. I've redrawn our object and our table with our force of gravity, and I've sort of simplified it. I've taken out all the other forces. So we know that that initial angle, the angle of the table with whatever's under it, is 35 degrees. I've drawn a straight line, basically whatever surface the table is resting on, underneath the surface of the table. And notice that when we meet the force of gravity, that forms a right triangle. So since that first angle is 35 and the next one is 90, the angle there, shown in purple, has to be 55 degrees. Okay, fantastic. Well, the force of gravity that's coming straight down intersects the line of the table in such a way that we know that this angle has to be equal to the 55. Well, that nails things down, doesn't it? Because that angle's 55, and the force of gravity on the y and the force of gravity on the x make a 90-degree angle. We know that this angle here, the one between the force of gravity and the force of gravity on the y, has to equal the slope of the table. It's 35 degrees. Or you can just commit to memory that that's equal to whatever the slope with ground is, and call it a day. That means that we have our angle here. We can go ahead and calculate the force of gravity times the cosine of theta, which is, of course, 22 newtons times cosine theta. The force of the table on the book is 18 newtons up. 22 newtons times the cosine of 35 is just a little bit over 18. Let's call it a rounding issue. So what does that mean? Well, it means that the sum of forces on the y, once we account for sig figs, is 0. Well, honestly, does that meet your expectations? Did the problem say anything about the book floating up into the air or sinking through the table? No? Then you knew already that the sum of forces on the y-axis had to be 0. Well, that means that the x-axis must be where all the action is. Let's go there. Okay, just as we said that the sum of forces on the y is basically equal to all the forces up minus all the forces down, when we're on the x-axis, the sum of forces on the x is going to be all the forces to the right minus all the forces to the left. Now, because of the direction that the box is pointing here, I might want to switch that and say all the forces to the left minus all the forces to the right. Actually, in this case, it might make more sense to say all the forces upslope minus all the forces downslope, or just draw your darn drafting table the other way. But, whatever. So, what does that give us? Well, sum of forces on the x here is equal to the force of friction, which is upslope, minus the force of gravity on the x. What? We can't have gravity on the x-axis? That's heresy, honestly. Next, they'll be burning you at the stake. Well, as a matter of fact, if you look carefully, because of the slope here, there is a force of gravity acting on the same axis as the tabletop. Well, that's why things slide down tables. Duh. So, sum of forces on the x is equal to that frictional force, 11 newtons, minus the force of gravity times sine theta. That means sum of forces on the x equals 11 newtons minus 22 newtons times sine 35, 11 minus 12.618. So the sum of forces on the x is negative 1.618, blah, 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 newtons, and that is down slope. So what does that mean? We found the net force on the x? Well, it means yes, the book will slide down the table because there's a net force on it. Now, here's what we would never do. We would never, ever draw that into our free body diagram, but we could say that the net force was 1.6 down slope. Okay, you've got practice problems in your book. The 4A problems are all assigned. Have fun!